in the next question, we ask to invert our correlation matrix, and then so that would give us the precision matrix. So I do that here using the solve function, and then we ask to multiply the correlation matrix with the precision matrix. So that's done here, and then vice versa, multiply the precision matrix by the correlation matrix, and that's done here. And finally we ask to do the LU decomposition on the matrix, and I chose to do the LU decomposition on the precision matrix. For LU decomposition, I wrote this function, which is called LU underscore decomp, which as a result gives me both parts, the lower part and the upper part of the matrix that was decomposed. And just to prove that the functions work correctly, I multiply the two parts together, the lower part and the upper part, and I get the original matrix, which essentially proves that the function works. Moving along, the next question is to use this mass package and try to fit an exponential distribution to some variable from the training set, which is right skewed, and see if that provides a good approximation to the data. So I chose the ground living area variable, and I use that for the fit distribution function from the mass package to get the optimum value for the lambda, and here's the value, and then I do side-by-side comparison of the two histograms, so the actual data from the ground living area versus the fitted distribution. And I mean, there is somewhat a resemblance between the two distributions. However, when we do further analysis, it turns out the distribution is the actual distribution is closer to normal distribution rather than exponential one. So I explained that here, where we're asked to find the 5th and 95th percentile of the exponential distribution, and this gives us a very wide range of values. If we compare and then next we ask to generate the same basically interval using the normal distribution, assuming normality. What is what would be the 5th and the 95th percentile? So using the normal distribution, we would get a much narrower range of numbers for the 5th and the 95th percentile. And finally, we ask to find the 5th and 95th percentile of the actual data itself. So that gives us the numbers which are closer to the normal distribution, the numbers that we got from normal distribution, rather than the numbers that we got from the exponential distribution. And to further illustrate that the variable is closer to the normal distribution, I have this chart histogram of the data and superimpose the blue line of the normal distribution, and the red lines indicate the 5th and 95th percentile of the data of the normal distribution. So here I'm stating that even though the ground living area variable appears to be right skewed, we come to the conclusion that it's more closely resembling a normal distribution still rather than the exponential one. So we finally come to the fourth and final part of the project, which is to do the multiple regression model and try to predict the house prices and submit that results to Kaggle competition. So I chose quite a wide selection of features from the training set to start with. As evident from here, I have quite a few features selected. I then decided to impute some of the missing data in the lot frontage because I thought that would be one of the important features for the model, which was missing some of the data, a small portion of the data. So in this case I decided to use the mean value for the data that was available, and to use the mean value for the missing entries. And then I decided to create two derived additional features. One for the age sold. Essentially, it's the difference between the year that the property was sold and the year it was built, +1. So I did +1 just to make sure it stays well above 0. And similarly, I'm calculating the age of basically how long ago the remodeling was done on the house, which I thought might also be a good indicator for the model. In some cases, like a ground living area and so on, in some of the numeric variables, I decided to standardize or rescale the values just so to improve the model results. And I wrote this standard scalar function, which basically subtracts the mean value from the observed value, and then divide that by the standard deviation. So that basically ensures that the feature values are centered around 0 and have a variance of 1. So finally, I built a linear model, linear regression model, using all these features, and look at the summary of the model. And then I noticed that there are a bunch of variables that gave basically were insignificant in predicting. So I decided to remove several variables by looking at the p-value. So if the p-values are too high, that means that there's very little chance that the predictor is meaningful. So instead of updating the model, I decided, I'm just gonna rebuild the model again by removing certain features that were not meaningful. So I do that here, and again look at the summary, but then I notice it did improve my model, but there's still quite a few features that could be removed by looking at the p-value again. So I find the feature with the largest p-value and update the model. So in here, for example, I removed in my first iteration I removed the total rooms above ground variable because that had the largest right here, that had the largest p-value, and it wasn't marked as significant at all. So I go through several of these iterations, essentially doing the what's called backward elimination process, and cleaning up the model in hopes of improving it. So essentially I got to my final model, which I then analyzed by looking at the plot of the residuals and see if there's a if the residuals are uniformly distributed, and also sorry, not uniformly, normally distributed. And the QQ plot here shows pretty much that a large portion of the residuals fall in line, and with some flare-ups on the edges, which is expected given the large data set. So once I was happy with the model, I decided to use it to predict. So here I'm loading the test data set, and I'm going to be using the same features that I used in my training, and I'm going to apply the same transformations of imputing the missing data, of deriving, of creating the derived features, and also performing the same rescaling that I've done during training. And finally, I call the predict function based on my model and the test data set, and get my predicted sale price, and generate the new IDs as expected for the Kaggle submission. So here's the head of the results, which shows the ID in the sale price columns. So I save the results into CSV, and here I present the summary of my predicted sale price, and also side-by-side comparison of the prices, of predicted prices versus the prices during training. And the shapes are somewhat similar, which indicates, which is a good indicator that the predictions were pretty much close. It's just that maybe I'm not too much off target, I should say, and feel some confidence in the predicted prices. So here is I submitted the results under this username, and my score was 0.42341, which wasn't that great, but at the same time wasn't that terrible either. So so I'm pretty much happy with the results of the prediction. So that's that. Thanks.